This conference will now be recorded.
All right, everybody, this is the section 3.3 video, and I need to start off doing example 3 again. We did this one in class, but I reversed something on part C, so I want to talk about that and why we were going through it kind of quick because I knew we had to catch up, and I said something backwards, so we need to change the answer to part C. So the graph of the first derivative of the function is shown below. The first question was, on what intervals is f increasing or decreasing and why? And remember, we said that this was the function that is f prime of x. Remember, this is the first derivative. They're asking me about f. And we did this part right in class. It was f prime of x is greater than 0, means that the original function was increasing, and f prime of x is less than 0 is when the original function is decreasing. So notice that just means above or below the x-axis. So we said that we were increasing because we're above the x-axis from 0 to 1. We were also above the x-axis from 5 to 7. So those are both increasing for the original function. And then everywhere else, we were below the x-axis on our first derivative. So that means we had negatives, remember, there for our slopes. So that means that we were decreasing on 1 to 5 and 7 to 8. Okay. Then it said, at what values of x does f have a local max or min, and why? Remember, we said that that would have been at those x-intercepts here, because remember, the x-intercepts we get for the first derivative came from hilltops and valleys on the original function. Those are the places where we had 0 for our tangent. Then that was for the slope of the tangent. So for part B, we had x is possible at 1, 5, and 7. Those are places where we would have possible local maxes and mins. And if you check your sign changes, this was up, this is down, so that goes from increasing to decreasing. That one is a local max. This goes from decreasing to increasing in terms of, remember, the slope of the tangent. So this one was a local min. And this one went again from positive to negatives. So that slope of the tangent went from increasing to decreasing. So that made that a local max. Okay, and here's where I went sideways in class, because remember, we ended up drawing the second derivative just so you guys could see what the second derivative would look like, but I wasn't paying attention and we answered for the second derivative. We are needing to know the intervals where f is concave up or concave down and why. So that is based on when is this graph decreasing or increasing for the first derivative. So if the first derivative, or excuse me, if the second derivative is going to have negative slopes, essentially, because remember, these are also going to be the slopes of kind of, if we were imagining tangent lines at each of these points, those slopes are either going to be positive or negative or 0, and that relates to that second derivative, okay, if we were going to graph that. So if f double prime is less than 0, we know that we were going to be concave down on f, the original function. If f double prime of x is greater than 0, then we know that on the original function, we were concave up. So the big thing was I just drew the second derivative to kind of show you guys how you could draw it, but then we forgot to remember that we were doing f. So concave down is when we're going to have decreasing slope for f prime, and concave up is we're going to have increasing slope for the f prime here. Okay, so that's related back to, if you were to draw this derivative, remember that if you're downhill, you're going to end up below the x-axis. If you're uphill here, you're going to end up above the x-axis for your second derivative. But that doesn't tell us about f. So we have to remember that it's based on those signs. So since we are negative from 0 to 2, that means we're going to be concave down from 0 to 2 on the original function. And since we are 2 to 3, we are increasing. We're going to be concave up from 2 to 3. Okay, and then from 3 to 4, we're going back down for our first derivative. So all those tangents are negative. So that means that graph will relate back to being a negative f double prime. So that's going to be concave down again. So that's from 3 to 4. We go uphill from 4 to 6. So that's going to end up being concave up. and from 6 to 8, we go back downhill. So that's going to be concave down. So the big catch was that we had to realize that this is still relating back to f, not the actual second derivative picture we drew in class. And then it says, what are the x-coordinates of the inflection points? Remember, those would be places where you would have a derivative where your slope of the f prime of 0 is equal to, f prime of x is equal to 0. So remember, we said those were those little max and mins on the first derivative. So that happened at 2, 3, 4, and 6. So I apologize, for making that boo-boo in class. But let's move on because we had two other examples that I needed to talk about in this video. We were running short on time because we're still playing catch up a little bit. So we did not do this one together. We're trying to find the intervals on which f is increasing or decreasing, the local maximums and minimums, and we're also values of f, and the intervals where there is concavity, which means concave up or concave down, and then the inflection points. Okay, so our first step here is going to be to take the first derivative of this function. So we want f prime of x. Now you might want to rewrite this as parentheses cosine x squared minus 2 sine x, just so you can see that's a chain rule right here. So when we take the first derivative, we pull the 2 power to the front. We still have our base of cosine x now to the first, and then we have to times that by the derivative of cosine x, which is negative sine x. So by our chain rule. And then we have minus 2 sine x. We need to take the derivative of that. So that's going to be negative 2 cosine x. So if we rewrite this, this is negative 2 cosine x sine x minus 2 cosine x. And remember, we're only looking at this at one revolution around the unit circle. So it's on that closed interval. So we need to figure out when does f prime of x equal 0 to find our critical numbers, because this is not going to have any undefined areas for our derivative, since cosine and sine are both continuous everywhere on the real number line and differentiable everywhere on the real number line. So we're definitely good in this interval. So this would be negative 2 cosine x. We'll pull that out as a GCF. So that's going to be sine x plus 1. Okay, so if we set each of those equal to 0, and we solve them, this is asking us really when does cosine x equal 0, and this is asking us when does sine x equal negative 1. So from 0 to 2 pi, that happens not very often, because remember, we don't need the plus 2 pi in because we're not going multiple revolutions. So the only place that cosine can be equal to 0 happens at two locations, remember, on the unit circle. That is when our x-coordinate is 0, so that happens at 0, 1, and at 0, negative 1, which is related to pi over 2 and 3 pi over 2. Okay. And then sine x equaling negative 1, that's when your y value is negative 1. That only happens in one place. So that is also 3 pi over 2. So that's the same answer twice. So we're only going to write it once when we do our check. So what we need to do is we need to figure out if these are increasing or decreasing on either side of these two values, and we want to evaluate that. So let's look at our first derivative. Check. So remember, I like to put pi over 2 here. It's the smaller of the two, then 3 pi over 2. These are our intervals then. So this is from 0 to pi over 2. This is from pi over 2 to 3 pi over 2. And from 3 pi over 2 to 2 pi. Okay. So remember, I'm not including brackets here because when you talk about something increasing or decreasing, it doesn't technically increase or decrease at an endpoint. So we're leaving that as open parentheses. Now, a value that is between 0 and pi over 2, we could use pi over 4. A value between pi over 2 and 3 pi over 2, we can use pi. And something between 3 pi over 2 and 2 pi, we could use, I think I used 7 pi over 4. Okay. So if we plug those into this, remember that we're considering plugging it into our derivative. This is negative 2 cosine x times sine x plus 1. So if you plug in pi over, first of all, the negative 2 is going to be negative. So the first sign is going to be negative in all three of these. Okay. Cosine of pi over 4 is positive, and sine of pi over 4 is a positive, plus 1 would still be positive. So this is negative times positive, so that comes out as a negative, which means our function's derivative is negative there, which means our original function is decreasing. Okay, then we plug in pi. Cosine of pi is -1, so that's going to be a negative. And sine of pi is 0, so that's going to be 0 plus 1, so that's going to be a positive. Two negatives multiply together make a positive, which means in this region we are increasing. And then on the last region, if we plug in 7 pi over 4, that's a cosine in quad 4. That would be positive. And sine of that would be negative square root of 2 over 2 plus 1. But negative square root of 2 over 2 is less than 1. So when you add 1 to it, it ends up still being positive. And so this multiplies to an overall negative, which means we are decreasing in that region. So what we know so far is that our function f is decreasing on the regions 0 to pi over 2 and 3 pi over 2 to 2 pi. And it is increasing from pi over 2 to 3 pi over 2. Okay. Now, when we talk about local maxes and mins, we have to look at these critical numbers and say, did we have a change in signs from increasing to decreasing? This one went from decreasing to increasing, so notice that is a local maximum. Now remember, when we wrote this in class, we said it's a local maximum value, and we put a blank because we don't actually know what that is yet. We don't know the y-coordinate for that, but it happens at an x of pi over 2. And we'll figure this out in just a second. And this goes from increasing, sorry, I wrote that backwards. I said minimum first and I wrote max. Sorry. So this is a minimum because notice it's the bottom of the hill. We have a local max because this goes from increasing to decreasing. So notice that's a maximum, a hilltop, and that is going to be a local max value of something at x equals 3 pi over 2. So remember, WebAssign is only going to be asking you for that min value and max value. They're asking you for the y-coordinate. To find those, you have to plug pi over 2 and 3 pi over 2 back into your function. So f of pi over 2 is cosine of pi over 2 squared minus 2 times sine of pi over 2. Okay, so at pi over 2, cosine is 0, so this is just 0 squared. And at sine of pi over 2, we get a 1, so this is 2 times 1, so this is just going to be -2 overall. So that minimum value is a -2. To get the max value, we have to plug in the 3 pi over 2. So this is going to be cosine of 3 pi over 2, and then we square it, minus 2 times sine of 3 pi over 2. So cosine of 3 pi over 2 is 0 still, so 0 squared. But this time, sine of 3 pi over 2 is -1. So we get minus 2 times -1, so it's going to end up being +2. Excuse me. Okay, so now we come to the point where we're going to have to take that second derivative to figure out where is our original function f concave up or concave down, and what are those possible points of inflection. So the big thing about this is that I'm going to change colors. So we're going to go with purple this time. We need to take that first derivative, and you can take it in its nicest form if you want. So if you want, you could take it in the factored form right here. So this is f prime of x was -2 cosine x times sine x plus 1. So now we want to take the derivative of this. So f double prime is going to be first, which we're going to consider this first. So -2 cosine x times derivative of the second. So this guy is just derivative of sine x because that will be 0. So that's just going to be cosine x plus second times derivative of the first, which is going to be a -2 still is there, and then we take the derivative of cosine, so that's going to be negative sine x. Okay, so if we clean this up a little bit, this is -2 cosine squared x. I'm going to put plus 2 sine x times sine x plus 1, and then I'm going to distribute that. So that's plus 2 sine squared x plus 2 sine x. And typically in a scenario like this, since this is not the Pythagorean identity because that one's negative and this one's positive, what I would want to do is get everything in terms of either sine or cosine. And since I have a sine x, I'm going to go with sine. So we're going to use our Pythagorean identity that says, I'm going to write it up here, cosine squared x is 1 minus sine squared x. So we're going to replace the cosine squared x. So that's negative 2 times 1 minus sine squared x plus the 2 sine squared x plus 2 sine x. Then we have that this would turn out as negative 2 plus 2 sine squared x plus another 2 sine squared x plus 2 sine x. Combining like terms, we get 4 sine squared x plus 2 sine x minus 2. And then I can factor this and set it equal to 0 now. So I'm going to pull out a 2 first. So that's 2 sine squared x plus sine x minus 1. And then you're trying to factor that piece. Now, if you haven't done factoring for a while with trig, remember you can kind of come over to the side and think of those as like u's. And you're just factoring this guy, but U stands for sine x. So this is, factor by grouping if you want to use a procedural method, or you can do trial and error. You end up coming up with, once you factor this though, you get a 2u minus 1 and a u plus 1. So notice you can check that real quick. That's 2u squared plus 2u minus u, which gives me plus 1u, and then minus 1. So this is going to factor, and I'm going to have to scroll down a little bit, into 2 times 2 sine x minus 1, and then sine x plus 1. Okay, so if we set each of these equal to 0, which 2 equal to 0 doesn't give us anything, but if we set sine x, 2 sine x minus 1 equal to 0, that would give us sine x equals 1/2. And if we set this one equal to 0, that's sine x plus 1. So that's when does sine x equal negative 1? And we know that this guy was 3 pi over 2. We already solved that in the last piece. And this one is going to happen at 2 places. Remember, sine is positive in quad 1 and 4. And it has a y value of 1/2 when it has a longer x. So notice that's going to have a short y. That's the 30 degrees. So that's pi over 6 and 5 pi over 6. Okay, so pi over 6, 5 pi over 6. So here's what we know so far. We were able to take the first derivative, we found the critical values, and we tested on each side and determined whether they were local maxes or local minimums. We ended up taking the second derivative, we set each part equal to 0, we solved, and these are what we call the possible points of inflection. Now notice I say possible points of inflection because this one right here should not be a point of inflection because it was already defined as a maximum. It was a local maximum here. So I'm still going to do the test to show you this, but you'll notice that there is not going to be a change in the sign of concavity for this guy. Okay, and that's because it's already been defined as a local maximum. So it doesn't technically end up being both. It can't be a point of inflection and a local maximum. So let's talk about this. So this one gets a little trickier in just one regard. So we're going to talk about how I could analytically talk about one of these because it's hard to find a test value. So if you put down pi over 6, and then the next biggest number would be 5 pi over 6, and then of course 3 pi over 2 is the biggest. Okay, so that makes this 0 to pi over 6, and pi over 6 to 5 pi over 6, and 5 pi over 6 to 3 pi over 2, and 3 pi over 2 to 2 pi, okay, because we went from 0 to 2 pi for our function. So these are actually pretty easy. I can find test values between pi over 6 and 5 pi over 6. In fact, pi over 2 is between those because that's in quad 1 and that's in quad 2. Between 5 pi over 6 and 3 pi over 2, we can actually use pi. And between 3 pi over 2 and 2 pi, we could use, again, 7 pi over 4. The bad one is 0 to pi over 6, because on our unit circle, pi over 6 is the smallest one right after 0. So we're going to talk about this one last. I'm going to tell you why. I'm going to do it more analytically, and you can apply this analytic approach in certain situations for the other ones as well. You don't technically always need the test value if you can compare what are the signs doing. So we'll talk about this in a second. I mean, if you wanted to pick pi over 12 or something smaller than pi over 6, you'd have to have a calculator to be able to do the evaluation by hand. So we're just going to run through these real quick, and then I'm going to talk to you about this first region, okay? So if we plug in, so remember this is our factors, 2 sine x minus 1 and sine x plus 1, okay? So notice if we have the 2 is always going to be positive, so that's going to start us off with a plus in each of these. You don't technically need to include that unless it's negative, but I always in the habit of doing all of my factors. And then pi over 2. So pi over 2 for sine, remember, is a 1. So this is 2 times 1 minus 1, so that's going to be positive. Okay, sine of pi over 2 is positive, and you add a positive to it, so it's 1 plus 1, that's going to be 2, also positive. So notice in this region we get 3 positive, which means it multiplies to a positive, and that region is concave up. Okay, if we plug in pi, sine of pi is 0, so this becomes 2 times 0, and then that would be minus 1, so that's actually going to be negative 1, so it's going to be negative. Sine of pi is, again, 0, but it's going to be plus 1, so it's going to come out positive. So we get 1 negative, which makes the overall region negative, which means this region is concave down. 7 pi over 4, we already plugged it in for the first guy. If you do sine of 7 pi over 4, that is a, because that is in the fourth quadrant, that's going to be a negative square root of 2 over 2. And then that's still going to be negative minus again, so it's going to end up being negative. And then sine of 7 pi over 4 is negative square root of 2 over 2, and that is smaller than 1. So if you add a positive 1 to it, it's going to end up positive. So what you notice is that sine x plus 1, and this has just happened in every single time we've done this, is always greater than or equal to 0. Because the only time it could be 0 is if sine x comes out as a negative 1. And that's the lowest sine x ever gets on a graph. So this can never be a negative sign. So if you noticed, anytime we plugged in sine x plus 1, we always ended up with a positive sign. So that at least tells me that first part right there. Okay, and we know that the 2 is positive. So all we need to determine for this region is what's that middle sign doing. So first of all, let me go ahead and multiply this one out. This is negative, which means this region is also concave down. Okay, so let's talk about that first region. This was 0 to pi over 6. So if you imagine 0 to pi over 6, what are our values doing here? Well, from here to here, x's and y's are always positive, right? So that means sines and cosines are always positive here. So when we think about this, we're saying what's happening in this specific region. We're questioning, is 2 sine x minus 1 going to come out positive or negative here? So this is more like saying, is sine x, remember it's equal to 1/2 here. What we want to know is sine x greater than 1/2? Is it going to come out positive, or is sine x less than 1/2? Well, if you think about the ordered pair at pi over 6, that is the ordered pair square root of 3 over 2 and 1/2. When you move to pi over 4, which is kind of elevated, this is square root of 2 over 2, this is square root of 2 over 2. When you move to pi over 3, you get a 1/2 and a square root of 3 over 2. So notice the x values are getting smaller as we go this way, and the y values, so they're getting smaller and smaller, the y values are getting bigger. So because this ends at 0, or excuse me, 1, 0. So I said that backwards, sorry. These are getting smaller in this direction, and these are getting smaller in this direction. Okay, so sine x, which is this value right here, between here, it's going to be less than. See that? Because you're going from 1/2 down to 0, so that means we're going to be doing less than 1/2. So that means that sign, when you work it out, this first value right here is going to be smaller than that -1. So we're going to get a negative sign overall. So let me just recap that to make sure you understood what we're saying. If you look at your unit circle and you have your points listed out, you notice that as we move towards pi over 2, the x's get smaller, but the y's get bigger. but between 0 to pi over 6, all of my y values are between 0 and a half. So at this point right here where we stopped our interval, we know that everything for sine below that is going to be less than 1/2, which means when we plug it back in, we're going to get a negative sign there. If it had been greater than 1/2, we would have gotten a positive sign there. So this comes out to an overall negative, which means it is concaved down. Okay, so why did we do all this? Well, first of all, they asked us about concavity. So where did I put my other information? So this was the information we got from the first derivative up here. And now we want to talk about concavity. So this function, f, is concave up on the following regions, from pi over 6 to 5 pi over 6, and also that's it. So that's the only one. Okay, we are concave down from the following: 0 to pi over 6, from 5 pi over 6 to 3 pi over 2, and from 3 pi over 2 to 2 pi. Okay, now we said that this guy was a max. We saw that from the last thing. And notice there's no change in the concavity. It's down, down. Where we get points of inflection is where our bowl flips. So in other words, we go from concave down to concave up, or concave up to concave down. So notice since this changes, that means there is a point of inflection at pi over 6. This also changes, so there's going to be a point of inflection at 5 pi over 6. So I know that I have points of inflection at pi over 6, comma something, we're going to have to find that in a minute, and 5 pi over 6. And if you want the actual ordered pairs, you have to go back to your function and plug them in. So let's look at our original function and copy that down again. So it was cosine squared x minus 2 sine x. So cosine x is squared minus 2 sine x. So let's plug these in. So cosine of pi over 6, we're going to square that, minus 2 times sine of pi over 6. So remember, cosine of pi over 6 is the square root of 3 over 2, and we're going to square that. And then times 2 times sine of pi over 6, which is 1/2. So this ends up being a 3/4 minus a 1. So that equals negative 1/4. So that is one of my points of inflection. If I plug in 5 pi over 6, I'm going to get cosine of 5 pi over 6. Then we're going to square it, minus 2 times sine of 5 pi over 6. So this guy ends up being a negative square root of 3 over 2, because it's in quad 2 and it's a cosine, squared. And then minus 2 times sine of 5 pi over 6 is again 1/2. Now when we square that, we still get the same thing. We get 3/4 minus 1. So this is also negative 1/2, or 1/4, sorry. Talking and writing is sometimes a challenge. So there is my concave up, concave down, and my point of inflection. Okay. All right, so that leads us to the last problem in this section, which kind of got overwritten into this. We needed to talk about this graphing problem. So this is saying sketch the graph that has the following information. I'm going to kind of try to box this off from that. Okay, it has to have all these conditions. So let's talk through what the conditions say. So it says f of 0 equals f prime of 0 equals f prime of 2 equals f prime of 4 equals f prime of 6, and those all equal 0. So what that tells me is that, remember, anytime your f primes equal a 0, that means that you have either a maximum or a minimum at those x values. So at x equals 0, 2, 4, and 6, we're either going to have, remember, maximums or minimums. Okay. We also know that f of 0 equals 0. That is an ordered pair. So that means that ordered pair 0, 0 is on our graph. Okay. This says our first derivative is greater than 0 if we're between 0 and 2 or 4 and 6. So when we look at that, that means that, remember, if you have a f prime greater than 0, you are increasing. So that means our graph should be increasing on 0 to 2 and 4 to 6. Our f prime of x is less than 0, which means our slopes are decreasing. So our original function is decreasing from 2 to 4 and 6 to, I guess, infinity. They didn't give us a stopping point. Okay. The double prime of x is greater than 0, means we are concave up. So we are concave up on 0 to 1 and 3 to 5. We are going to be having an f double prime that is less than 0, so that means we're going to be concave down from 1 to 3 and 5 to infinity. And then this last statement is to make sure you understand something we teach you in both 136 and 137. If you plug negative x into a function and you get the original function back, that means that your function is even. Now, what is an even function? An even function has y-axis symmetry. So everything they told us was about the positive side of this graph because we were using all positive x values, but we'll know that we can completely reflect the graph across the y-axis. So it's going to be the same pattern on the other side. So let's see if we can sketch out what this graph would look like. Now, the only thing we don't really know is we don't know how high or low all the other values are getting. So we're kind of having to guesstimate on some of that. So this says, and this just has to be a function that satisfies all of the given conditions. So as long as we kind of follow all of our properties, we should be okay. So we know that 0, 0 is on the graph. That was because f of 0 was equal to 0. We also know that somewhere else we're going to have maxes and mins. So at 2, 4, and 6, and 0. So since 0 is got itself being a max or min as well, why not let 2 go up from here? Now, the reason I'm doing that is because I also know my function is increasing from 0 to 2. So I know I have to go uphill. So that makes this have to be a minimum because it is lower, and this one has to be a maximum. And then at 4, we would need to go back down. And I'm going to keep it the same height as this one because they can have that nice symmetry. It makes it easier to graph the other side. And then 6 is our other one. So 5, 6, let's go back up and have a max. Now, here's how I know if I've done this right. Let's check. I'm increasing from 0 to 2. I'm decreasing from 2 to 4. So notice that had to go back down and be a minimum. I'm increasing from 4 to 6, and I'm decreasing from 6 to infinity. So we'll have to draw that out. Now, I'm concave up from 0 to 1. So notice that means from 0 to 1, you have to draw it as if the bowl is facing upward. At 1 to 3, we flip. So now we're going to be concave down. So notice from 1 to 3, my graph is concave down. From 3 to 5, so here's 4, here's 5, I'm going to be concave up again. So 4, oops, not paying attention to where I'm drawing. We have to actually touch our point. So we're going to hit this, and then we're going to go up again until 5. And then we have to be from 6 to infinity, we're going to be concave down. So that just means it keeps going down forever. Okay. Now, this is, let's just make sure we verified all the information. F of 0 equals 0. Yep, that's on the graph. We have f prime of 0, f2 prime of 2, f prime of 4, f prime of 6 are all equal to 0 as well, which means those slopes are 0, which means they are minimums or maximums locally. And like I said, we haven't finished the graph yet. Are we increasing from 0 to 2? Are we decreasing from 2 to 4? Increasing from 4 to 6? Decreasing from 6 to infinity? Concave up, so bowl is up from 0 to 1. Bowl is down from 1 to 3. Bowl is up from 3 to 5. Bowl is down from 5 to infinity. Now, the last feature said that this was an even function. So all I have to do to finish is I have to scale this out on the other side and make it symmetric. So that means at -2, we would have that maximum again. At -4, we would have that minimum. At -6, we would have the maximum again, and then it would go down forever. So this is a graph that satisfies all of the conditions that were listed out. And that is the end of the section 3.3 notes.